325 years of silence. That's not reassurance. That's a debt. The night of January 26, 1700, Cascadia ruptured. The tsunami it generated killed hundreds in Japan, a country 5,000 miles away that never felt a single tremor. Just the water, arriving without warning. Since 2019, GPS and seismic data show Cascadia and San Andreas correlating at levels never recorded in 50 years of modern monitoring. Two fault systems moving together for the first time. The tremors aren't the threat. What they're doing to the stress inside both faults is... What happens if Cascadia doesn't fall alone? Before we go any further, if this matters to you, hit like and subscribe. It takes 2 seconds, and it's what keeps this going. Let's find out. Drive from the redwood forests of Northern California, up through Oregon's rain-soaked coast, past Washington's jagged inlets, all the way into British Columbia, and what you'll see is one of the most breathtaking stretches of land on Earth. Volcanic peaks draped in snow, bays so still they mirror the sky, forests so dense they block out noon sunlight. It's stunning, genuinely stunning, and it is built on ground that should not be trusted. From Cape Mendocino in Northern California to the southern tip of Vancouver Island, you're looking at roughly 1,800 kilometers of coastline sitting directly above one of the most geologically volatile systems on the planet. This isn't metaphor. This isn't alarmism. The land beneath those redwoods, beneath those mirror-flat bays, beneath those cities, Seattle, Portland, Eugene, Victoria, is actively deforming. Right now, quietly, continuously. 60 million people live here. Most of them have no idea what's happening under their feet. To understand the anomaly, you first have to meet the two fault systems at the center of this story. And I want you to think of them not as geological abstractions, but as characters, because they each have a personality, a history, and a breaking point. The first is the Cascadia subduction zone. You cannot see it. That's part of what makes it so unsettling. It doesn't announce itself with a visible scar or a dramatic ridge. It hides roughly 80 to 150 kilometers offshore, running parallel to the coastline from Northern California all the way up to British Columbia, a 1,000-kilometer-long collision zone buried beneath the Pacific Ocean floor. Here's what's happening down there. The Juan de Fuca Plate. A relatively small oceanic plate is being shoved eastward by the spreading ridges of the deep Pacific. It hits the edge of the North American plate, and because oceanic crust is denser than continental crust, it loses that contest. It gets forced downward, subducted. The Juan de Fuca Plate is literally diving beneath the continent at roughly 4 centimeters per year, the approximate speed your fingernails grow. That sounds slow. It is slow. But multiply that speed by 10,000 years, and you begin to understand the scale of accumulated force we're talking about. The interface between these two plates, the zone where one grinds against the other as it descends, is called the megathrust. It's a fault surface that stretches across hundreds of kilometers, and it is, in the most precise geological sense, locked, not moving freely, stuck. Two massive slabs of rock pressed together with incomprehensible force, friction holding them in place, while the slow, relentless movement of the plates continues trying to push them apart. That tension has to go somewhere. It doesn't disappear. It stores. The second character is the San Andreas Fault. Unlike Cascadia, San Andreas doesn't hide. It announces itself. Drive south from San Francisco, and you can literally see it, a long, straight valley cutting unnaturally through the coast ranges. The Carrizo Plain in Central California exposes it with brutal clarity. 2 offset stream channels, a ridge that runs in a line too straight to be natural. The land itself visibly sheared apart on either side. It runs 1,300 kilometers from the Salton Sea in the south all the way to Cape Mendocino in the north. The same Cape Mendocino where our story begins. the same place where San Andreas ends and Cascadia begins at a single chaotic intersection of tectonic plates called the Mendocino Triple Junction. San Andreas is a strike-slip fault. The two plates on either side, the Pacific Plate to the west, the North American Plate to the east, aren't colliding head-on. They're grinding past each other laterally. Los Angeles is on the Pacific Plate. San Francisco is on the North American Plate. Over millions of years, Los Angeles has been slowly moving north toward San Francisco at about 5 centimeters per year. In roughly 15 million years, they'll be neighbors. That's cold comfort for everyone living there now. These two fault systems, Cascadia offshore and San Andreas onshore, have defined the geological identity of the American West Coast for millions of years. And for the entire duration of modern seismic monitoring, roughly 50 years, they've been treated as separate problems, independent systems, risks to be assessed in isolation. That assumption is now being questioned. In the past 18 months, seismologists monitoring the PNSN, the Pacific Northwest Seismic Network, have been looking at something that doesn't fit the expected pattern. Microseismic activity along both fault systems has increased, but not in ways that correlate with volcanic activity in the Cascades or with tidal loading cycles, which are the two most common natural explanations for short-term fluctuations in seismic background noise. The algorithms designed to detect statistical anomalies in seismic data are flagging elevated activity, not screaming red, not a crisis, but a consistent, persistent deviation from the established baseline that hasn't resolved on its own the way normal fluctuations typically do. The seismologists are watching carefully. But to understand why that matters, why a quiet uptick in microseismic noise is worth a video this long, you need to understand what normal actually looks like in this region. And the answer will surprise you. Most people assume that a quiet fault is a safe fault. No shaking, no problem. The ground isn't moving, so everything must be fine. That's exactly backwards. In the physics of fault systems, silence isn't safety. Silence is accumulation. The quieter a locked fault has been, the more energy it may have stored and the more violent its eventual release could be. Understanding this requires knowing what the baseline actually looks like, because without a baseline, you can't recognize when something is wrong. Let's start with Cascadia. On any given year, the Cascadia subduction zone produces hundreds of small earthquakes, mostly magnitude 1 to 2, sometimes a cluster of M3s, occasionally a M4 that people near the epicenter might feel as a brief, dull thud. These micro-events are normal, expected. They represent tiny stress releases along secondary faults and the edges of the main locked zone. The seismic networks record them automatically. The algorithms process them, and unless something unusual appears in the pattern, nobody outside the monitoring community pays much attention. Below the threshold of instrumental detection, even smaller things are happening. The Juan de Fuca plate is flexing as it bends downward into the mantle. Fluids water that's been trapped in the oceanic crust gets squeezed out as pressure increases with depth. Those fluids migrate into the surrounding rock, subtly altering its mechanical properties. This is the background hum of a subduction zone, constant, complex, largely invisible. What's not invisible, what's become one of the most important discoveries in Cascadia science over the past 2 decades, is something called a slow slip event, or SSE. Every 12 to 15 months, a section of the Cascadia fault does something remarkable. It slips. Not violently, not catastrophically, but it moves. The plate interface shifts by centimeters over a period of weeks. If this happens suddenly, it would be a major earthquake. Instead, it unfolds so slowly that seismometers barely register it. The only instruments sensitive enough to reliably detect it are GPS receivers, which can measure ground displacement to within a few millimeters. When a slow slip event occurs under Cascadia, the land near the coast actually moves slightly westward backward toward the ocean as the fault temporarily releases a small fraction of its stored stress. Then it locks up again, and the accumulation resumes. This is normal. This is Cascadia breathing. The critical context is what those SSEs are not releasing. The fault interface between the Juan de Fuca plate and the North American plate is estimated to be locked across a zone hundreds of kilometers wide and potentially 60 to 80 kilometers deep in places. The SSEs happen at the deep, transitional edge of this locked zone. They don't touch the main, fully locked section where the catastrophic energy is stored. That section hasn't moved in 325 years. Now San Andreas, different architecture, different personality, same fundamental problem. Unlike Cascadia, San Andreas is partially visible and partially active in ways that give it a misleading reputation for being manageable. Near the town of Parkfield in Central California, there's a segment of the fault that creeps continuously. It slips freely and slowly at the surface, releasing stress gradually, producing small earthquakes on a semi-regular schedule. Scientists have studied Parkfield for decades precisely because it's so well behaved. It's the cooperative student in a classroom full of troublemakers. The troublemakers are the locked segments. The Hayward Fault, a major strand of the San Andreas system running directly beneath Oakland and Berkeley, last ruptured in 1868. That's 156 years of accumulated stress. Geologists estimate it produces a major earthquake every 140 years or so on average. Do that math. The northern San Andreas segment offshore of San Francisco, which ruptured in 1906, has been rebuilt by ongoing tectonic motion for over a century. The southern San Andreas near Los Angeles, the most seismically dangerous fault segment in California, is estimated to have a recurrence interval of roughly 150 to 200 years for a major rupture. The last one was in 1857. That's 167 years ago. Here's the number I want to stay with for a moment. Geologists working with the USGS estimate. There's roughly a 60% probability of a magnitude 6.7 or larger earthquake hitting the greater Los Angeles area within the next 30 years. For a M7.5 or larger on the southern San Andreas specifically, some models put the probability in the next 50 years above 50%. For Cascadia releasing a full margin M9, the estimated probability per 50-year window ranges from 10 to 15%, which sounds low until you realize that's comparable to the lifetime risk of developing certain cancers that we take extremely seriously. None of these numbers mean an earthquake will happen tomorrow. Probability doesn't work that way. What they mean is that both systems are operating in a window of statistical vulnerability past due by some measures, accumulating energy that cannot stay stored forever in a region where the population and infrastructure exposure have never been greater. And here's what makes the current moment different from any other point in modern monitoring history. The background noise isn't behaving the way established models predict it should. Microseismic activity has deviated from expected patterns in ways that don't correlate with the usual suspects. The deviation is small, but it's persistent, and it's showing up on both systems, not just one. A long silence on a locked fault isn't reassurance. It's a debt. And debts don't disappear, they compound. Now that you know what normal looks like, the baseline, the expected rhythms, the numbers that define what quiet is supposed to mean, we can talk about what's happening beneath the surface, the actual physical machinery. Let me give you a picture. Imagine a sheet of tempered glass, not window glass. The thick engineered kind used in structural panels and car windshields. You can press on it, you can bend it slightly, you can apply enormous sustained force, and it will hold and hold and hold, giving you absolutely no visible signal that anything is wrong. No gradual cracking, no slow deformation you can watch and prepare for. It stores the stress internally, invisibly, right up until the moment it doesn't. And when that moment arrives, it doesn't crack from one corner and spread slowly. It shatters completely, instantaneously, across its entire surface in a fraction of a second. That is how the Earth's crust fails under tectonic stress. Not gradually, not with warning proportional to the violence of what's coming. It holds, 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 and then breaks all at once. Rock under long-term tectonic loading behaves elastically, like a spring being compressed. The surrounding crust bends, distorts, strains, storing energy in its own deformation. Friction along the fault interface is what keeps the system locked. And here's the thing about friction at geological scales. It doesn't weaken slowly as stress increases. It holds near its maximum capacity right up until it fails. And when it fails fast. The rupture propagates along the fault plane at roughly 3 kilometers per second. The ground on either side lurches. Everything stored in decades or centuries of elastic strain releases as seismic waves in a matter of seconds. By the time you feel the shaking, the fault has already moved. You're feeling the echo. Now Cascadia and San Andreas both run this same fundamental machine, but they run it in completely different configurations. And that difference is everything. The Juan de Fuca plate is being driven eastward by the spreading ridge far out in the Pacific. When it reaches the continent, it loses the density contest. Oceanic crust is heavier than continental crust and gets forced downward. Diving beneath the North American plate at a shallow angle, the contact surface between these two slabs, where one grinds against the other as it descends, is the megathrust interface. It is locked. Two planetary scale slabs of rock held together by friction, while the relentless geometry of plate tectonics keeps trying to pull them apart. The North American plate above gets dragged inward and downward, compressed, bent, loaded like a bow being drawn over centuries. When that lock breaks, the bow releases. The North American plate snaps back. The seafloor above the rupture zone surges upward not by centimeters, by meters across hundreds of kilometers of fault length. Simultaneously, that upward displacement of the seafloor shoves the entire water column above it upward with it. The ocean surface lifts. That energy propagates outward as a tsunami. In the open ocean, it's barely visible, a long, low pulse of displaced water, maybe half a meter high, but carrying momentum through thousands of meters of depth. Then it reaches the coast. The seafloor shallows. The wave slows at its base and piles upward. It can reach 15, 20, 30 meters, depending on the shape of the bay or inlet it's entering. That is Cascadia's release mechanism. Vertical, upward, oceanic. The energy goes into the water column and becomes a wave. San Andreas works nothing like that. There's no subduction. The Pacific plate and the North American plate aren't converging. They're sliding laterally past each other, like two massive slabs of coarse sandpaper pressed hard together and dragged in opposite directions. Where the fault is locked, that lateral motion is prevented. Stress accumulates in the surrounding rock, straining the crust elastically on both sides over years and decades. When the fault finally breaks, the two sides don't move up or down relative to each other. They lunge sideways. In 1906, ground on the west side of the fault moved up to 6 meters northward, relative to the east side in under a minute. Roads, stream channels, fence lines crossing the fault were offset by that distance before anyone understood what was happening. The energy San Andreas releases is horizontal. The seismic waves that cause structural damage, shear waves. Surface waves travel through the ground and shake buildings laterally. Structures are engineered to carry vertical loads, to resist gravity pulling them straight down. Horizontal shaking is a categorically different problem. It's the force that drops bridges, shears off building columns, ruptures pipelines, and causes unreinforced masonry to collapse floor by floor. No tsunami from San Andreas. But shaking across an area that dwarfs most people's mental model of a local earthquake. The 1906 rupture was felt from Oregon to Los Angeles. So here is the critical distinction. And I want you to hold this clearly. Cascadia releases energy vertically. The threat goes into the ocean and becomes a wave that hits the coast. San Andreas releases energy horizontally. The threat travels through the ground and destroys what's built on it. Two different energy signatures, two different damage profiles, two different populations at primary risk, though with significant geographic overlap. When both systems activate in close temporal sequence, not necessarily simultaneously, but within hours or days of each other, those two damage profiles don't stay neatly separate. They interact across shared infrastructure. Coastal roads needed for tsunami evacuation get damaged by inland fault rupture. Buildings weakened by one fault's shaking fail sooner under the others. Emergency response systems built around single event scenarios get pulled in contradictory directions simultaneously. The compounding isn't additive. It's multiplicative in ways that are genuinely difficult to model. But this is only the surface physics. Geological history will show you the true scale of what can actually happen. The physics tells you how these systems work. History tells you what they actually do to people. And the historical record here is not ambiguous. These faults have broken before. They've left evidence in sediment cores, in drowned forests, in century-old photographs, in bureaucratic damage reports written by people who survived, and that evidence speaks clearly about scale, not worst-case speculation. Documented reality. Start with the oldest entry in the record. The night of January 26, 1700 on the Pacific Northwest coast, the Cascadia megathrust ruptured. Indigenous communities along the shores of what is now Oregon and Washington felt the ground shake with a violence their oral histories would preserve for generations. Then the ocean came, inland. Not a wave in any ordinary sense, the water simply rose and kept rising, flooding river valleys and low coastal lands in the darkness. Nobody in North America wrote it down. There was no written record to make. But on the other side of the Pacific, there was. On the morning of January 27, 1700, a tsunami struck the coastline of Japan. No preceding earthquake that anyone in Japan had felt. No warning, just water. Arriving. Japanese officials documented it in the systematic way they recorded all significant natural events. They called it an orphan tsunami, a wave with no identifiable parent. That orphan sat unexplained in Japanese archives for nearly 300 years. It wasn't until the 1990s that geologist Brian Atwater and a team of researchers assembled the pieces matching the Japanese records with geological evidence found along the Pacific Northwest coast. The travel time of the wave from the rupture zone to Japan, combined with its recorded height on the Japanese coast, allowed them to reconstruct the source event, a magnitude 9.0 to 9.2 rupture along nearly the full 1,000-kilometer length of the Cascadia megathrust. The evidence on the American side is still physically present. Drive to certain stretches of the Washington or Oregon coastline and walk into the tidal marshes. You'll find ghost forests, stands of western red cedar and Sitka spruce, dead, bleached to silver. Roots still anchored in soil that dropped by 1 to 2 meters in a single night 325 years ago. When Cascadia ruptured, the coast didn't just shake, it subsided. The land sank suddenly. Salt water flooded in, and the trees died standing where they had grown for centuries. Their preserved remains are still there, silent, specific, unmistakable. That is what Cascadia does. That fault, currently 325 years into its next interseismic period, with no indication in the geological record that it ever waited this long between full ruptures. Now, move the clock forward 2 centuries. April 18, 1906, San Francisco. Population roughly 400,000, the largest city on the American West Coast. Prosperous, architecturally ambitious, thoroughly accustomed to thinking of itself as permanent. At 5:12 in the morning, the northern section of the San Andreas Fault ruptured along approximately 470 kilometers. The shaking lasted 45 to 60 seconds, less than 1 minute. When it stopped, 80% of the city had been destroyed. The earthquake itself toppled buildings and shattered the water distribution system. The fires that followed ignited by broken gas lines, unchecked because firefighters had no water pressure burned for 3 days. Around 3,000 people died. More than 225,000 were left homeless. In a city of 400,000, that means more than half the population lost their homes from less than a minute of ground motion. I want you to update that number for today. The San Francisco Bay Area now holds approximately 7.7 million people. The infrastructure is incomparably more complex, more layers of interdependent systems, more people living in areas that didn't exist in 1906, and the Hayward Fault, running directly beneath Oakland and Berkeley, last ruptured in 1868. 156 years of accumulated stress on a fault estimated to break on a roughly 140-year cycle. The southern San Andreas near Los Angeles last ruptured in 1857, 167 years ago, on a fault with an estimated recurrence interval of 150 to 200 years. Both segments are past due by their own geological averages. Then 2011, and this one I want you to sit with, because this is your reference point for what a Cascadia rupture means for the Pacific Northwest coast. March 11th, 2011. The Tohoku earthquake struck northeastern Japan at magnitude 9.0 to 9.1, a subduction zone event. Same fundamental mechanism as Cascadia. Oceanic plate diving beneath continental plate. Megathrust interface failing. Seafloor displacing upward. Tsunami generated. The shaking was severe and caused significant structural damage across a wide area. But the earthquake wasn't what defined that disaster. Japan had spent decades preparing for exactly this. Seawalls up to 10 meters high along hundreds of kilometers of coastline. A nationwide early warning system capable of pushing tsunami alerts to mobile phones within 2 to 3 minutes of rupture detection. Evacuation maps distributed to every household in coastal zones. Regular community drills. Japan was, without serious dispute, the most tsunami-prepared nation on Earth at the time of that earthquake. Nearly 20,000 people died. The seawalls were overtopped. In certain coastal inlets, where geography concentrated and amplified the wave, water reached 40 meters above sea level. The warnings worked. People received them, but for residents in the lowest coastal zones, 2 or 3 minutes was not enough time to reach high ground on foot. The wave arrived before they could get there. 20,000 people who received accurate warnings and still couldn't survive. Now, look at Oregon and Washington through that lens. There are no seawalls along the Pacific Northwest coast designed for Cascadia-scale inundation. The Shake Alert early warning system is still being deployed and has coverage gaps. FEMA's own hazard assessments acknowledge that multiple coastal communities in Oregon and Washington sit in tsunami inundation zones where vertical evacuation to high ground, within the available time, is not physically achievable for the full population on foot. Many coastal evacuation routes cross low bridges that would likely sustain damage or fail outright in the same earthquake that generates the tsunami. Those routes are meant to help people escape. Oregon's state geologist has said publicly that a full Cascadia rupture would be the worst natural disaster in North American history, not a projection. A consequence assessment based on the fault's known geometry and the coast's documented vulnerability. The warning window between the end of ground shaking and first wave arrival at many Oregon and Washington coastal locations is 15 to 30 minutes. In Tohoku, with the best warning infrastructure ever constructed, that margin cost 20,000 lives. On the Pacific Northwest coast, it is not a more forgiving margin. In many places, it is tighter. 3 events, 3 data points from the actual historical record. 1700 tells you what Cascadia does to a coastline. 1906 tells you what San Andreas does to a city. 2011 tells you what a subduction zone tsunami does, even when the affected society has done everything humanly possible to prepare. History has made clear what has already happened, but the real question is, can these 2 systems actually trigger each other? And this is where science begins entering genuinely unsettling territory. The history is clear. The physics is established. Now look at what's actually happening right now, across multiple points on the map, simultaneously, because that's where this story stops being purely academic and starts being something you should pay close attention to. Start at the southern end of San Andreas, the Salton Sea region, at the fault's extreme southern terminus in California, has been registering elevated microseismic activity over the past 18 months. That detail matters more than it might seem, because this particular stretch of fault has a documented history of behaving as a trigger point. In 2010, a magnitude 7.2 earthquake struck near Baja California, just south of the Salton Sea area, and the stress redistribution from that event produced a detectable uptick in seismicity northward along the San Andreas system. The fault doesn't just sit there passively. When its southern end gets agitated, that agitation has a way of propagating. What's being recorded now isn't a single large event. It's a patterned clusters of small earthquakes, M2 and M3 range, occurring with a frequency and spatial distribution that deviates from the expected background rate. Not dramatically, but persistently. The kind of deviation that, if it appeared in a patient's vital signs, would make a doctor order more tests rather than send the patient home. Move north along the Cascades, the volcanic chain that runs parallel to the coast through Oregon and Washington, sitting directly above the descending Juan de Fuca plate. Geothermal monitoring stations have recorded elevated heat flow and increased hydrothermal activity at several locations along this chain in the same period. Volcanic systems in subduction zones are intimately connected to the mechanical state of the subducting slab beneath them. Fluids released from the descending plate feed the magma systems above. When those fluid dynamics change, the volcanic systems respond. The Cascades aren't showing signs of imminent eruption, but they are registering a shift, and that shift is time correlated with the other signals. Then there's the GPS data from Northern California. A network of continuously operating GPS receivers, precise enough to measure ground movement to within a few millimeters, has recorded surface deformation patterns in Northern California that don't match the expected output of standard tectonic models for this period. The ground is moving in ways that the models, fed with historical data, didn't predict for this specific window. That doesn't mean the models are wrong about everything. It means something in the current stress state of the crust isn't fully captured by the historical baseline those models were built from. Each of these signals, taken alone, could be explained away. The Salton Sea cluster could be routine seismic noise. The Cascades geothermal shift could be seasonal or hydrological. The GPS anomaly could reflect groundwater changes or post-seismic adjustment from older events. Scientists are rigorous about this. They don't panic over individual data points. They look for convergence, multiple independent lines of evidence pointing in the same direction at the same time. That's what's making some researchers uncomfortable right now. Not one signal, several, distributed across the system, showing up in the same 18-month window. And then there's the edge event that ties it together geographically. The Mendocino Triple Junction, the chaotic intersection point where the Pacific Plate, the North American Plate, and the Juan de Fuca Plate all meet, where San Andreas terminates and Cascadia begins, where the geometry of three converging tectonic systems creates mechanical complexity that researchers are still working to fully characterize, has been producing seismicity at elevated rates. This junction is never quiet. It generates its own earthquakes routinely, its own stress field, its own peculiar brand of geological instability. But the rate and spatial pattern of recent activity there has drawn attention from monitoring teams at both the USGS and the Pacific Northwest Seismic Network. Precisely because the triple junction is the mechanical bridge between the two systems at the center of this story, pull back further. Widen the frame to the entire Pacific Ring of Fire, the 40,000-kilometer belt of subduction zones, volcanic arcs, and transform faults encircling the Pacific Basin, and the picture gets harder to dismiss as local noise. New Zealand has registered increased seismic activity along its alpine fault system. Japan continues to process the seismic consequences of Tohoku's massive stress redistribution, with ongoing sequences in regions that had been relatively quiet. Alaska's Aleutian subduction zone has produced several significant earthquakes in the past 2 years. Mexico's Pacific Coast subduction system generated a magnitude 7.6 event in 2022 and has maintained elevated background seismicity since. These are not all connected in some simple, linear way. The Ring of Fire is not a single fault. It's a collection of independent systems sharing a common tectonic driver, the ongoing contraction of the Pacific Basin as the Pacific Plate subducts around its margins. But when multiple segments of a globally interconnected stress system show simultaneous deviation from their respective baselines, the scientific question that follows is legitimate and serious. Is this coincidence? Or does it reflect a large-scale redistribution of stress at the plate boundary scale that's expressing itself at multiple locations simultaneously? That question doesn't have a definitive answer yet. The honest answer is that the data is suggestive but not conclusive. Researchers are actively debating it. What's not being debated is whether the question is worth asking, because the alternative, assuming that multiple simultaneous anomalies across a connected system are all independently coincidental, requires its own justification. To answer that, we need to go deep inside the Earth to where the force is actually generated. Most people think of fault ruptures as local events. The fault breaks here, the shaking happens here, and then it's over. The energy dissipates, the fault settles into its new position, and the rest of the geological world goes on unchanged. That's not how it works. When a fault ruptures, it doesn't only release energy at the rupture site. It redistributes stress throughout the surrounding crust, sometimes across distances that would seem implausible if they hadn't been directly measured. Understanding that redistribution mechanism is the key to understanding why the simultaneous signals across Cascadia and San Andreas are more than coincidental noise, and why researchers at places like Caltech and the USGS are running the specific calculations they're currently running. The mechanism is called Coulomb stress transfer. The name is more intimidating than the concept. When a fault slips, the rocks on either side of it move into new positions. That movement changes the stress state of the surrounding crust, not just immediately adjacent to the rupture, but across a much wider region. Some faults in that region get pushed further from failure stress is removed from them. Others get pushed closer to failure stress is added. Whether a given fault is loaded or unloaded depends on its orientation relative to the rupture and its position in the stress field that the rupture creates. This is not theoretical. It has been measured directly, repeatedly, in the aftermath of large earthquakes. After the 1992 Landers earthquake in Southern California, researchers mapped the pattern of subsequent seismicity in the region and found that earthquakes in the following years clustered preferentially in areas where Coulomb stress transfer calculations predicted stress had increased. The areas where stress should have decreased showed reduced seismicity. The correlation was striking enough to shift how the seismological community thinks about fault interaction. What's changed in the past 2 decades is our understanding of how far this effect reaches. Early models suggested that Coulomb stress changes became negligible at distances beyond a few fault lengths from the rupture. More recent work, incorporating better data and more sophisticated modeling, has pushed that boundary significantly outward. A major rupture doesn't just affect its immediate neighborhood, it modifies the stress field across a region that can span hundreds of kilometers, sometimes more, depending on fault geometry and the mechanical properties of the crust between the source and the target. For Cascadia and San Andreas, separated by a shared boundary at the Mendocino Triple Junction, rather than any significant distance, this matters considerably. But Coulomb stress transfer is a static effect. It describes the permanent stress change after a rupture. There's a second mechanism that operates dynamically, while the seismic waves from a rupture are still traveling, and this one is in some ways even more striking. Dynamic stress triggering works differently. The seismic waves generated by a large earthquake, particularly the long-period surface waves that travel efficiently across vast distances, can temporarily alter the stress state on faults they pass through. The wave doesn't have to be large by the time it arrives. Even a small dynamic stress perturbation, if it arrives at a fault that's already close to its failure threshold, can be enough to tip it over. The evidence for this is not hypothetical. In November 2002, a magnitude 7.9 earthquake struck on the Denali Fault in Alaska, a strike-slip fault in the interior of the state, thousands of kilometers from California and Yellowstone. Within days of that rupture, seismologists detected triggered microseismic activity at Yellowstone, over 3,000 kilometers away. They detected it along segments of the San Andreas system in California. The surface waves from the Denali earthquake, traveling at roughly 4 kilometers per second, had passed through those regions and perturbed faults that were already sitting near their stress limits. 3,000 kilometers. That's the demonstrated range of dynamic stress triggering from a single large earthquake. Cascadia and San Andreas share a plate boundary junction. They are not 3,000 kilometers apart. They are mechanically adjacent. Now bring in the Caltech modeling work. Because this is where the numbers become specific in a way that's hard to set aside. Computer simulations of a hypothetical Cascadia M9 rupture full margin, 1,000 kilometers of megathrust braking simultaneously calculate the resulting Coulomb stress change on the northern segments of the San Andreas system, particularly the section running through the Bay Area at between 0.1 and 0.3 bars. That sounds like a small number. In absolute terms, it is a small number, but context is everything here. The threshold at which geologists consider a Coulomb stress increase to be seismically significant, capable of materially advancing the timing of a rupture on a receiving fault, is generally cited at around 0.1 bar. The numbers coming out of the Caltech models sit right at and above that threshold, applied to fault segments that are already, by every available metric, deep into their accumulated stress cycle. Think of it this way. Picture a room filled with dominoes, each one standing upright, each one representing a fault segment under accumulated stress. Most of them have been standing for a long time. Some have been standing long enough that a light breeze could knock them over. You don't need to push every domino. You don't need enormous force applied everywhere. You need to find the right domino, the one already leaning, and apply just enough perturbation at the right moment. The system does the rest. One falls into the next, and the geometry of the arrangement determines how far the cascade runs. A Cascadia rupture would not be a light breeze. It would be a 0.1 to 0.3 bar Coulomb stress increase, delivered dynamically through seismic waves and statically through permanent crust deformation, applied to fault segments that the available data suggests are already close to their failure thresholds. The domino that's been standing for 167 years. The one that's been standing for 156 years? Right there, at the other end of the room. But this machine is only dangerous if the systems are synchronizing with each other, and recent data is showing worrying signs of exactly that. The domino analogy gets you partway there, but it assumes each domino is independent, that they only interact at the moment of collision. What's emerging from the data is something more unsettling than that. It suggests the dominoes may already be leaning toward each other, slowly, subtly, across decades, before any single one falls. This is the concept of seismic synchronization, and it sits at the frontier of what fault system research is currently wrestling with. In classical physics, we tend to think of independent systems as staying independent unless something large and obvious connects them. But complex nonlinear systems, where the components interact through multiple feedback loops, where small inputs can produce disproportionate outputs, don't always behave that way. They can synchronize through weak coupling. Two pendulums hanging from the same beam will, over time, begin to swing in phase with each other, not because any large force is deliberately coordinating them, but because the tiny mechanical vibrations they share through the beam are enough to gradually pull their rhythms into alignment. The coupling is small. The effect, given enough time, is not. Fault networks are nonlinear systems. They're coupled through the crust they share, through the stress fields they generate, through the slow redistribution of tectonic load across interconnected plate boundaries. The question researchers have been asking carefully, with appropriate skepticism, is whether the Cascadia and San Andreas systems show any statistical signature of this kind of coupling, whether their activity levels have been moving in ways that are more correlated than independent systems should be. The time series analysis covering the period from 2019 to 2024 is what makes this conversation worth having right now. When seismologists apply cross-correlation analysis to the activity records of both systems, looking at whether elevated activity in one system tends to be accompanied by elevated activity in the other, across timescales ranging from days to months, the correlation coefficient for this 5-year window comes out higher than for any comparable period in the 50-year instrumental record, not dramatically higher, not a number that announces itself with alarm, but statistically distinguishable from what you'd expect if the two systems were genuinely operating independently. 50 years is not a long data set by geological standards. The researchers running this analysis are the first to say so, but it's the data set we have, and within it, the 2019 to 2024 window stands out. What that cross-correlation means mechanically is still being debated. Correlation in a dataset doesn't automatically establish physical causation, and the researchers involved are not claiming it does. What they're saying is that the statistical pattern is consistent with a coupled system, one in which the state of Cascadia's stress field and the state of San Andreas's stress field are not fully independent of each other. Whether that coupling is strong enough to matter operationally, whether it reflects genuine mechanical interaction or some shared external driver like fluid pressure changes or seasonal loading, is an open question. But the pattern is there, and it wasn't there at this level before. Now layer on the threshold concept, because this is where the synchronization data stops being an abstract statistical curiosity and becomes something concrete. Every fault segment has a failure threshold, a level of accumulated stress beyond which the frictional resistance holding it locked can no longer be maintained. Below that threshold, the fault stays locked regardless of small perturbations. A tidal loading cycle, a nearby small earthquake, a seasonal change in groundwater pressure. These things happen constantly, and at low stress levels, they produce no effect. The fault is stable. The perturbation is absorbed without consequence. But as accumulated stress pushes a fault segment toward 90%, 95%, 99% of its failure threshold, that stability degrades. The fault becomes increasingly sensitive to exactly the kinds of small perturbations it would have ignored at lower stress levels. A M3 earthquake that would have been irrelevant a century ago becomes potentially significant if the receiving fault has been building toward rupture for 150 years. A change in pore water pressure that would normally be geological background noise becomes a meaningful input when the fault is already at 98% of failure. This is what geophysicists mean when they describe a fault as being critically loaded. It's not a metaphor. It's a specific mechanical condition in which the margin between the current stress state and the failure threshold has narrowed to the point where ordinary small-scale perturbations, the kind that happen continuously in any active tectonic environment, are no longer guaranteed to be inconsequential. By the available estimates, multiple segments of both the Cascadia system and the San Andreas system are in or approaching that critically loaded condition. The Hayward Fault has been building since 1868, the southern San Andreas since 1857, the Cascadia megathrust since 1700. These are not systems sitting comfortably in the middle of their stress cycles. They're systems operating in the late stages of their interseismic periods, where the physics of threshold behavior means that the effective trigger threshold has dropped significantly below what it was a century ago. The GPS data makes this concrete in a way that's harder to dismiss than any statistical analysis. Continuously operating GPS stations distributed along the West Coast measure ground displacement to millimeter-level precision. And what they've been recording in recent years doesn't fully match the predictions of standard interseismic coupling models, the models built from decades of historical deformation data to predict how fast strain should be accumulating on each fault segment. At several locations, the ground is deforming faster than those models predict. Not dramatically faster, but measurably, consistently, persistently faster than the historical average would suggest. That deviation means stress is accumulating at a rate that the baseline models, calibrated to earlier decades of data, didn't fully anticipate. Whether that reflects a real change in coupling behavior, a limitation in the historical data set used to build the models, or some transient effect from factors like groundwater depletion or post-seismic adjustment from other events. All of those possibilities are on the table. But the measurement itself is not in dispute. The ground is moving faster than expected at certain segments, and faster accumulation at segments that are already late in their stress cycles means those segments are potentially closer to their thresholds than the standard models would place them. The Earth is loading both systems at the same time, with a statistical correlation between their activity levels that hasn't been this high in the modern instrumental record. And while the Earth is accumulating energy this way, the human defensive layer is moving in exactly the opposite direction. The geological picture is sobering enough on its own, but it sits inside a human context that makes it considerably worse. Because while the fault systems have been quietly loading toward their thresholds, the society built on top of them has been doing something that should concern you deeply. It has been expanding its exposure while eroding its defenses. Start with the buildings, because this is where the gap between what we know and what we've done about it is most stark. Tens of thousands of buildings across Seattle, Portland, and San Francisco were constructed before 1980. That's the dividing line that matters here. 1980 is roughly when modern seismic building codes, informed by the engineering lessons of the 1971 Sylmar earthquake and subsequent research, began to be meaningfully incorporated into construction standards across the West Coast. Buildings erected before that threshold were designed to different specifications. In many cases, they were designed to specifications that engineers today would describe as wholly inadequate for the ground motions these fault systems are capable of producing. Seattle's situation is particularly well documented and particularly uncomfortable. The city has formally identified more than 1,100 unreinforced masonry buildings, URM structures, brick construction without internal steel reinforcement within its limits. Structural engineers are not ambiguous about what happens to URM buildings in a major earthquake. They collapse, not might collapse, not are at elevated risk of collapse. The engineering assessment, based on the behavior of similar structures in past earthquakes, is that URM buildings fail in M7 and above ground motion with high reliability. Seattle has over 1,000 of them, many occupied, many in dense commercial and residential neighborhoods. The city has known about this for years. Retrofit programs exist. They're voluntary, underfunded, and proceeding at a pace that structural engineers describe, with notable restraint, as insufficient given the time frame of the risk. Portland has its own version of this problem. San Francisco, despite decades of seismic awareness and more aggressive retrofit mandates, still carries significant pre-1980 building stock in neighborhoods that would experience severe ground amplification in a major rupture on the Hayward Fault, which runs, it bears repeating, directly beneath Oakland and Berkeley, immediately across the bay. The warning systems designed to give people time to respond carry their own gaps. Shake Alert, the earthquake early warning system being deployed along the West Coast, represents genuine technological progress. When it works as designed, it can push alerts to phones and trigger automated safety responses, stopping trains, opening fire station doors, alerting hospitals seconds to tens of seconds before shaking arrives at a given location. In a large earthquake, those seconds matter, but the system's coverage is uneven. Its integration with critical infrastructure is incomplete, and for the communities closest to a fault rupture, the ones that would experience the most violent shaking, the warning time available is measured in single-digit seconds, which limits what any warning system can practically accomplish. The DART buoy network, the deep ocean tsunami detection system that monitors for the pressure signatures of tsunami-generating seafloor displacement, has experienced operational gaps in the offshore Cascadia region. Some buoys have recorded extended periods of degraded function or complete inoperability before maintenance could be performed. A detection network is only as reliable as its least reliable component, and in a system where the warning window is already 15 to 30 minutes, gaps in detection infrastructure translate directly into reduced warning time for coastal communities. The communities themselves are the third layer of the problem. A survey conducted by the Oregon Office of Emergency Management found that fewer than 20% of households in coastal tsunami inundation zones had a practiced evacuation plan. Not a written plan, a practiced one. The difference matters because in an actual event, the behavior that's been physically rehearsed is the behavior that gets executed under stress. Abstract awareness that a tsunami could occur is not the same thing as knowing exactly which route to take, on foot, in the dark, potentially after significant ground shaking has damaged roads and disoriented landmarks. With 15 minutes before water arrives, many coastal communities in Oregon and Washington sit in inundation zones where the terrain simply doesn't support rapid pedestrian evacuation to high ground within the available time window. The geography is what it is. Some of these communities have begun constructing vertical evacuation structures, reinforced towers designed to provide refuge above wave height for people who can't reach natural high ground in time. These structures exist in a handful of locations. The need vastly exceeds the supply. Meanwhile, Seattle's population has grown by 21% over the past decade. That growth has pushed residential and commercial development into areas that experienced engineers look at with genuine concern, particularly the tideflat zones around the south end of Elliott Bay, where the soil column consists largely of artificial fill and soft marine sediment that will liquefy under strong shaking. Liquefaction is not a minor inconvenience. It's a process in which saturated loose soil temporarily behaves like a liquid under seismic loading, causing buildings to sink, tilt, and collapse, and causing underground infrastructure pipes, cables, foundations to fail across wide areas. New construction is rising on these zones right now, some of it to modern seismic standards, some of it not. All of it adding population to areas that the geological hazard maps already flag in red. The psychological dimension of this compounds everything else. The longer a region goes without a major disaster, the more its population normalizes the absence of that disaster. Psychologists call this normalcy bias, the cognitive tendency to underestimate the probability of disruption because disruption hasn't happened recently within living memory. It's not irrationality. It's a predictable feature of how human risk perception works. But in a geological context, where the relevant recurrence intervals span centuries, normalcy bias means that the populations most at risk are precisely the ones with the least visceral personal experience of what the risk actually looks like. Nobody alive on the Oregon coast today was alive in 1700. The disaster that defines the worst-case scenario for their community happened before their grandparents' grandparents were born. That temporal distance makes the risk feel abstract in a way that profoundly shapes behavior, preparedness spending, political prioritization, and individual decision-making about where to live and whether to maintain a go bag. The Earth doesn't care about cognitive bias. It doesn't adjust its loading rate based on whether the people above it have updated their emergency plans. It just keeps accumulating stress at the pace that plate tectonics dictates, indifferent to whether the society on top of it is ready or not. But before we go into the scenarios, we need to stop and confront what science actually knows, and more importantly, what science still doesn't know. Let's clear the ground first. Every time a story like this circulates elevated seismic activity, anomalous GPS readings, correlated signals across multiple fault systems, a predictable set of explanations follows it into comment sections and forums. Hey, AP, underground weapons testing, deep oil drilling destabilizing the crust, government programs manipulating tectonic activity for reasons that vary depending on who's doing the theorizing. I'm not going to spend much time on these because they don't deserve much time, not out of dismissiveness, but because the evidence simply doesn't support them. HAARP is a high-frequency radio research facility in Alaska. It operates in the ionosphere. The ionosphere is approximately 60 to 1,000 kilometers above the Earth's surface. The seismic anomalies we've been discussing occur in the crust, 10 to 50 kilometers below the surface. The physical mechanism by which a radio transmission into the upper atmosphere could alter stress conditions in deep crustal rock doesn't exist in any framework of physics that has ever been validated by experiment. That's not a gap in our understanding waiting to be filled. It's a proposed mechanism with no supporting evidence and no plausible pathway. Underground weapons testing generates seismic signals, and those signals have a very specific signature: the frequency content, the waveform shape, the lack of aftershock sequences that distinguishes them clearly from tectonic events. Seismic monitoring networks were specifically designed and refined during the Cold War to make exactly this distinction for arms treaty verification purposes. The seismic signals being discussed in the Cascadia San Andreas context have tectonic signatures. That's not ambiguous. Oil and gas extraction can cause induced seismicity, and this is a real phenomenon that deserves real attention in regions where it occurs. Oklahoma's experience with wastewater injection-induced earthquakes over the past 2 decades is well documented and scientifically established. But the fault systems we're talking about here, the Cascadia megathrust, the main locked segments of San Andreas, are not in regions of significant oil extraction, and the scale of stress we're discussing, accumulated over centuries of plate tectonic loading, is orders of magnitude beyond what any human industrial activity has been shown to generate. These are purely tectonic dynamics. They operate on timescales that began millions of years before our species existed. The anomalies we're discussing are products of those dynamics, not of anything we've done or are doing to the crust. I say this not to provide reassurance. The tectonic explanation is, if anything, more concerning than a human-caused one, because it's not something we can switch off, but because accuracy matters. Conspiracy frameworks don't just get the cause wrong. They redirect attention and energy away from the preparation that would actually help. Now the harder part, the limits of what science actually knows. The most important thing I can tell you, with complete confidence, is this: nobody can predict when an earthquake will occur. Not within years, not within months, not within days, not with AI, not with supercomputers, not with any combination of sensor networks and machine learning that currently exists or is currently being developed. This is not a temporary limitation waiting to be overcome with better technology. It reflects something fundamental about how fault systems behave. They are sensitive to conditions at scales too small and too numerous to ever fully characterize, and small uncertainties in those initial conditions produce enormous uncertainties in rupture timing. The physics, at the level of actual fault mechanics, is genuinely chaotic in the technical sense of that word. Anyone who tells you they know when the next Cascadia earthquake will happen is wrong. Anyone who tells you a specific date or window based on pattern matching or numerical sequences or animal behavior is not doing science. There are no credible precursor signals reliable enough to support specific short-term predictions for any of the fault systems we've discussed. The scientific community has been trying to find such signals for decades. The honest summary of that effort is that short-term earthquake prediction remains unsolved, and the researchers working on it are the first to say so. The Coulomb stress transfer mechanism. I described earlier the process by which one fault's rupture loads stress onto adjacent faults is real and well established at the scale of regional fault networks over short distances. The specific question of how effectively that mechanism operates across the distance and geological complexity separating Cascadia and the main San Andreas segments is still actively debated. The Caltech modeling work that produces the 0.1 to 0.3 bar stress change estimates relies on assumptions about crustal structure, fault geometry, and friction coefficients that are reasonable but not perfectly constrained. Different modeling groups using slightly different assumptions produce different numbers. The range of published estimates is wider than a single figure suggests, and the lower end of that range overlaps with the threshold of seismic significance in a way that leaves real uncertainty about whether the effect would be large enough to matter operationally. The cross-correlation data showing elevated statistical coupling between Cascadia and San Andreas activity from 2019 to 2024 is intriguing. It's being taken seriously by the researchers who produced it. It is not yet peer-reviewed consensus. 50 years of instrumental data is a thin foundation from which to draw conclusions about systems that operate on century-scale cycles. The statistical pattern could reflect genuine mechanical coupling. It could reflect a shared external driver, Pacific-wide changes in plate loading rates, for example, that produces correlated behavior without direct interaction. It could reflect a coincidence that will look unremarkable in retrospect once the full data set extends another few decades. These possibilities haven't been ruled out. The interaction models for Cascadia and San Andreas are, by necessity, built partly on extrapolation. We have good data on how individual fault systems behave in isolation over the modern instrumental period. We have limited data on how they behave in combination. Because the kind of compound event we're discussing, a full Cascadia rupture, followed by triggered activity on San Andreas, hasn't occurred within modern monitoring history. We're modeling a scenario we've never directly observed with instruments, using physical principles that are well established, but applied to a specific configuration for which ground truth validation is impossible until the event actually happens. That is an honest description of where the science stands. Not nihilism, not dismissal of the evidence, just an accurate accounting of what we know confidently, what we think is likely, and what remains genuinely open. Within that open space, there are two variables that don't get enough public attention. And I want to spend a moment on each of them because they're the ones that could change the picture materially in the coming months. The first is slow slip events under Cascadia. You already know what these are: the silent, weeks-long creep episodes at the deep edge of the locked megathrust zone that GPS instruments detect as small backward ground movements along the coast. What's worth watching right now is not whether they're occurring. They occur regularly, predictably, every 12 to 15 months in most segments, but how they're occurring. The frequency of SSEs in certain Cascadia segments has been changing. Some segments are slipping more often than the historical average. Some are slipping with larger displacement than previous events in the same location. The tremor activity that accompanies these events, the low-frequency seismic tremor that marks fluid movement and microslip at the plate interface, has been registering at elevated levels in several segments. SSS don't rupture the locked zone. That point is important. The main megathrust, the section that generates M9 earthquakes, sits updip from where SSS occur. But SSS aren't entirely disconnected from the locked zone either. They transfer stress incrementally over multiple cycles. They reshape the stress distribution along the fault interface in ways that can subtly alter where the locked zone is most vulnerable. The change in SSE behavior being recorded right now may be inconsequential. It may also be a signal that the stress state at the deep edge of the locked zone is evolving in ways that deserve attention. The second quiet variable is pore fluid pressure. This one is genuinely underappreciated in public discussions of earthquake hazard, and that's partly because it doesn't have an obvious analog in everyday experience. Here's the concept. The rock along a fault plane isn't solid and dry. It's permeated by groundwater, fluids released from the subducting slab, hydrothermal fluids circulating through the crust. That water exists under pressure, and that pressure has a direct effect on the effective friction along the fault surface. Higher pore pressure effectively lubricates the fault. It reduces the normal stress pressing the two fault surfaces together, which lowers the friction force holding them locked, which lowers the effective failure threshold. Changes in groundwater conditions from drought, from heavy precipitation, from deep fluid migration associated with volcanic or geothermal activity, can alter pore pressure along fault segments in ways that are difficult to monitor directly and easy to underestimate in their mechanical significance. The Cascade's elevated geothermal activity, noted in Part 1 of this act, is relevant here. Increased hydrothermal circulation in a volcanic arc, sitting directly above a subducting slab, can change the fluid budget of the overlying crust in ways that ripple down to the fault interface. How much, and where, and whether it's enough to matter for near-term fault stability. These are questions that current monitoring cannot fully answer. These two variables, SSE, behavior, and pore fluid dynamics, are the quiet parts of the system. They don't make headlines. They don't show up in the seismic catalog in obvious ways. But they operate continuously. They influence the mechanical state of both fault systems, and they're changing in ways that the monitoring community is tracking with more attention than usual. That is the honest picture. The tectonic forces are real. The mechanisms are established. The data showing anomalous behavior is real. The uncertainty about what that behavior means for rupture timing is also real, and it's large. Both of those things are true simultaneously, and anyone who tells you otherwise in either direction, whether towards certainty of imminent disaster or certainty of no concern, is telling you something that the science doesn't actually support. With that honest picture in place, let's look at the two scenarios. From the quietest outcome to the most severe, the most statistically probable outcome of everything we've discussed is this: nothing catastrophic happens in the near term. I want to say that clearly, without burying it, because intellectual honesty cuts in both directions. We've spent a significant amount of time walking through the mechanisms of concern, the anomalous data, the gaps in human preparedness, the physics of how these two fault systems could interact. That picture is accurate, and it sits alongside another picture that is equally accurate: the base rate probability of a major rupture on either Cascadia or San Andreas in any given short window, months. A year, even a few years, remains low in absolute terms. Most periods of elevated microseismic activity in tectonic regions resolve without escalating into major events. Most statistical anomalies in seismic time series data turn out, in retrospect, to be noise in a complex system rather than signals of imminent catastrophe. That's not reassurance designed to send you away feeling comfortable. It's just the honest reading of what the numbers say. The most likely interpretation of the current activity pattern is that we're observing a normal expression of the seismic cycle, a period in which the fault systems are releasing accumulated stress incrementally through the very mechanisms that tectonic systems use to manage their energy budgets without catastrophic failure. Microseismic clusters like the ones recorded near the Salton Sea and the Mendocino Triple Junction occur regularly in active fault regions. They represent small stress adjustments, the fault system finding marginally more stable configurations without crossing any major threshold. The elevated cross-correlation between Cascadia and San Andreas activity could reflect a transient shared driver that will fade as the driving conditions change. The GPS deformation anomalies could be capturing a post-seismic adjustment from earlier events, or seasonal hydrological effects, or the tail end of a slow slip cycle rather than the leading edge of something larger. If this scenario plays out, and again, this is the statistically most likely near-term outcome, what you'd expect to see over the next 3 to 6 months is a gradual return of microseismic density to baseline levels across both systems. The Salton Sea cluster would quiet down. The Mendocino Triple Junction would settle back into its ordinary chaotic background activity. The GPS stations would stop showing anomalous deformation rates. The slow slip events under Cascadia would complete their current cycle and return to their expected recurrence pattern. The system would, in the language of geophysics, relax not permanently, not completely, but enough that the statistical deviation from baseline would no longer be distinguishable from normal background variation. This would not mean the underlying risk had resolved. That's an important distinction. The fault systems would still be where they are in their stress cycles. Cascadia would still be 325 years into its interseismic period. The Hayward Fault would still be 156 years past its last major rupture. The southern San Andreas would still be sitting on 167 years of accumulated strain. The debt doesn't get paid by a period of quiet. It gets deferred. The quiet period, if it comes, simply means the interest keeps accruing a little longer before the account comes due. But that deferral matters. It matters in ways that go beyond the obvious. Here is something worth sitting with, even if everything we've discussed resolves quietly over the next several months. Even if the monitoring data returns to baseline and this period of anomalous activity becomes a footnote in future research papers, the preparation work that individuals, families, and communities do right now retains its full value, completely, independently of whether any disaster materializes on any particular timeline. This is a point that tends to get lost in the way disaster risk communication works. The framing is almost always event-centric. Is an earthquake coming soon? Yes or no? And that framing makes preparation feel contingent on the answer. If the answer seems to be no, or not yet, the practical motivation to prepare weakens. People put the emergency kit back on the to-do list. The family evacuation conversation gets postponed again. The structural assessment of the older building gets deferred because there's no immediate urgency. But preparation doesn't work on the same timeline as threat assessment. A practiced evacuation plan has value for the entire time between now and the eventual rupture, which, whenever it occurs, will arrive without the courtesy of advance warning. An emergency kit stocked and accessible costs the same whether the earthquake happens next month or in 30 years. The households along the Oregon coast that have walked their evacuation routes that know exactly how many minutes it takes to reach high ground on foot from their front door, that have made the decision in advance rather than in the chaos of post-rupture seconds. Those households carry that knowledge as a form of insurance that doesn't expire and doesn't depend on any particular window of seismic activity to be worth having. The communities that survived Tohoku best were not the ones with the most sophisticated warning systems. They were the ones where residents had actually rehearsed what to do, where the decision to go to high ground immediately, without waiting for official confirmation, had been made in advance and internalized as a reflex. In some communities, children as young as 10 led elderly neighbors up evacuation routes because they'd practiced the route in school drills. Those children's preparation didn't depend on anyone having correctly predicted that March 11th, 2011 would be the day. If the current anomaly resolves quietly, that resolution doesn't teach us that preparation was unnecessary. It teaches us that we got a window, a period, when the mechanisms of concern were salient and visible and motivating, and what we did with that window is what will determine outcomes when the window eventually closes and the account eventually comes due. Because it will, the geological record on that point is unambiguous. The only variable is timing. And timing is the one thing we genuinely cannot know. There's a specific pattern worth recognizing here. Seismically active regions tend to have preparedness cycles that inversely track disaster memory. In the years immediately following a major earthquake, preparedness rates rise sharply. People retrofit buildings. Emergency kits get purchased. Evacuation drills increase. Then time passes. The visceral memory fades. The sense of urgency softens, and preparedness levels gradually decline right up until the next major event resets the cycle. This pattern has been documented in California after every significant earthquake sequence in the modern period. It reflects something true about human psychology, but it's exactly backwards from what geological reality requires. The period of apparent quiet is precisely when the next stress cycle is building. The time when it feels least urgent to prepare is often when the fault is most actively accumulating toward its next threshold. If scenario 1 plays out, if the system settles, the anomalies resolve, and the monitoring data returns to baseline over the coming months, the correct response is not relief, followed by reduced vigilance. It's continued, steady, undramatic preparation that doesn't require an emergency to justify itself. This scenario is likely, hold that. And hold simultaneously what it doesn't mean. It doesn't mean the risk has passed. It doesn't mean the debt has been paid. And it doesn't mean the next window of anomalous activity, whenever it comes, will also resolve quietly. At some point in the future, one of these windows will not resolve quietly. The geological record guarantees it. The only uncertainty is which window. But there is a second scenario, and this is the one that scientists don't want to say out loud, but their computer models cannot ignore. This is the scenario that doesn't appear in press releases. It doesn't get discussed at city council meetings about infrastructure budgets. It lives in the appendices of research papers, in the internal modeling runs at national laboratories, in the conversations that seismologists have with each other when they're not being careful about public communication. It's not suppressed. It's just uncomfortable enough that the people who understand it best tend to reach for cautious language when describing it in public. The computer models can't ignore it, so neither should you. What follows is not prediction. It's a physically coherent sequence grounded in established mechanisms, consistent with the data we've reviewed, constructed from modeling work that exists in the scientific literature describing what a cascade failure of both systems could look like if the conditions align in the worst way. I'm walking you through it step by step because the individual steps are each scientifically defensible. It's the combination that's never been formally modeled in its entirety, and that gap in our modeling is itself part of the story. Step 1 begins offshore, somewhere along the 1,000-kilometer length of the Cascadia megathrust, possibly near its southern end, where the stress gradients are steepest, possibly near the center where the locked zone is widest, possibly triggered by a slow slip event that nudges a critically loaded segment across its threshold. The interface fails, the lock breaks, the rupture propagates. Not slowly? At kilometers per second, the failure front races along the fault plane, unzipping the locked interface that has held since 1700. Depending on how much of the megathrust participates, whether this is a partial rupture of the southern segments at magnitude 8.5 or a full margin event engaging the entire system at M 9.0 to M 9.2, the duration of rupture, propagation, ranges from roughly 90 seconds to over 3 minutes. But the shaking at any given location doesn't last just for the duration of the rupture front passing beneath it. The seismic waves radiate outward, reflect off geological boundaries, get trapped in sedimentary basins, and produce ground motion that continues long after the fault has finished moving. In Seattle, Tacoma, and the surrounding Puget Sound region, that shaking lasts 3 to 5 minutes. Think about what 3 to 5 minutes of violent ground motion means structurally. The 1906 San Francisco earthquake lasted under a minute and destroyed 80% of the city. The 1964 Alaska Good Friday earthquake, the largest ever recorded in North America, at magnitude 9.2, produced shaking that lasted approximately 4 to 5 minutes across Anchorage. The damage was comprehensive and systemic, not building by building, block by block. The infrastructure that survived the initial shaking often failed in the extended motion that followed, as repeated stress cycles exceeded the fatigue limits of structures that might have survived a shorter event. Seattle's unreinforced masonry buildings, over 1,100 of them, formally identified, formally flagged, not yet formally retrofitted at adequate scale, begin collapsing in the first minute. The soft soil zones around Elliott Bay liquefy. Buildings on fill settle, tilt, sink. Water mains fracture across the city as the ground deforms, exactly as they did in San Francisco in 1906, eliminating fire suppression capacity at the moment it will be most needed. The Alaskan Way Viaduct's replacement infrastructure, the Highway 99 tunnel, performs according to its seismic design specifications, but those specifications were written for a specific ground motion envelope, and a full margin Cascadia event at close range may exceed them in certain frequency bands. Portland, further from the coast and sitting on a different soil profile, experiences severe shaking, but with a different character, longer period motion that is particularly damaging to mid-rise and high-rise structures, of which Portland has many. The Willamette River bridges, several of which predate modern seismic standards, are under immediate assessment pressure. And while the cities are still shaking, while the ground motion is still ongoing, the ocean is already moving. The seafloor along the rupture zone has lurched upward by several meters across hundreds of kilometers. The water column above it has been displaced. The tsunami is already propagating shoreward at the speed of a commercial jet aircraft. 15 minutes after the shaking stops in Seaside, Oregon, the water arrives in Cannon Beach, in Newport, in the coastal communities that FEMA's own inundation maps show receiving wave heights of 10 to 20 meters under full margin rupture scenarios. The 15 to 30 minute window. The one that Tohoku demonstrated is not sufficient even with the best warning infrastructure on Earth. That is step 1, Cascadia, alone. The event that Oregon's state geologist has already described as the worst natural disaster in North American history. Before any interaction with San Andreas is considered, step 2 begins in the minutes and hours that follow, as the seismic wave field from the Cascadia rupture propagates southward. The surface waves, the long period, far-traveling components of the seismic wave field that are most effective at dynamic stress triggering reach the Mendocino Triple Junction within minutes of rupture initiation. This is the junction we've returned to repeatedly throughout this story. And here is where its significance becomes concrete. 3 plates meeting at a single point, San Andreas terminating, Cascadia beginning. A stress field already complicated by the competing mechanical demands of 3 converging tectonic systems. The dynamic stress perturbation from a full Cascadia rupture arriving at the triple junction is not small. It's not the attenuated whisper of a distant earthquake. It's the wave field from one of the largest earthquakes geologically possible on the North American continent, arriving at the precise locations where the mechanical connection between Cascadia and San Andreas is most direct. The Coulomb stress change calculated for the northern San Andreas segments, the 0.1 to 0.3 bar range. From the Caltech models is the static component, the permanent stress redistribution that follows after the waves have passed. The dynamic component, while the waves are passing through, is larger and more immediate. The northern San Andreas, from the Triple Junction up through the Bay Area, receives both simultaneously. Step 3 is where the domino falls. The Hayward Fault has been accumulating stress since 1868, 156 years, on a fault with an estimated recurrence interval of around 140 years. The USGS Working Group places the probability of a magnitude 6.7 or larger on the Hayward at 33% in the next 30 years. But that probability is calculated from the baseline stress state, without conditioning on the occurrence of a full Cascadia rupture, delivering additional Coulomb stress directly to the fault system. When you add 0.1 to 0.3 bar of Coulomb stress to a fault already estimated to be at or past its average recurrence threshold, you are not adding a small perturbation to a stable system. You are potentially providing the final increment of loading to a system already at 99% of failure. The physics doesn't require a large trigger when the fault is that close to its limit. It requires only enough. The Hayward ruptures. Hours after Cascadia, or days, the models don't constrain the timing precisely. And that imprecision is itself informative about the limits of what we can calculate. But within the window that Coulomb stress transfer research suggests is most relevant for triggered seismicity hours to days following a major stress redistribution event, the probability of Hayward failure, conditional on a full Cascadia rupture, rises to levels that no responsible hazard assessment can set aside. The magnitude range is M7.0 to M7.8, depending on how much of the fault participates and whether adjacent strands activate sympathetically. Step 4 is the compounding. San Francisco and Oakland are not encountering a Hayward rupture in isolation. They are encountering it after the Cascadia surface waves have already passed through waves that, while insufficient to cause major structural damage at that distance from the source, are sufficient to have begun the process of fatiguing already marginal structures. Pre-1980 buildings in the East Bay that might have survived the Cascadia ground motion alone are now being subjected to a magnitude 7+ local event with epicentral distance measured in kilometers rather than hundreds of kilometers. The infrastructure is already compromised before the second event begins. The Bay Area's BART system, which runs through tunnels beneath the bay, has been stress tested by the Cascadia waves. The Bay Bridge, retrofitted after 1989 but operating in a seismic environment, now significantly more loaded than its design basis assumed. The hospital network, whose structural integrity determines whether the injured from a major earthquake can be treated, already activated, already resource strained from processing casualties and damage assessment from the Cascadia event, now facing a second mass casualty event generated locally. Emergency response, by definition, is a system that works by concentrating resources on a single event. Mutual aid flows from unaffected regions to affected ones. Federal resources mobilize toward a defined disaster zone. That model breaks when there are two simultaneous disaster zones of comparable scale, separated by 800 kilometers, each making demands on the same national response capacity at the same time. The FEMA estimate for Cascadia alone $32 billion in direct losses, approximately 13,000 deaths under a full margin scenario, was produced without incorporating triggered seismicity on San Andreas. That number was already the largest single-event natural disaster projection in American history. The compound scenario has not been formally modeled with a published damage estimate because the modeling requires assumptions about the timing and magnitude of the triggered event that current science cannot constrain precisely enough to produce a defensible single number. What the researchers who work on this will tell you, privately and carefully, is that the compound scenario exceeds any natural disaster framework that American emergency management has ever been designed to handle. The infrastructure consequences extend beyond the immediate damage zones. Interstate 5, the primary north-south transportation corridor connecting the entire West Coast, crosses multiple river systems on bridges whose seismic vulnerability has been assessed and flagged. Damage at even a few critical crossing points doesn't just inconvenience traffic. It severs the logistics chain that emergency response depends on for moving personnel, equipment, and supplies. The coastal rail lines face similar vulnerabilities at their lowest elevation crossings. The ports are a separate category of consequence. Seattle, Tacoma, and Oakland collectively process approximately 30% of all containerized imports entering the United States. Tsunami inundation affects the Seattle and Tacoma port facilities directly. Earthquake damage and liquefaction affect Oakland's terminal infrastructure. The supply chain disruption from extended closure of these facilities measured not in days, but in weeks and months. Because port infrastructure damaged by combined tsunami and seismic effects cannot be restored quickly, propagates through the national economy in ways that are difficult to bound from above. The federal electrical transmission infrastructure, the high-voltage lines that move power from generation sources in the Pacific Northwest down through California, follows corridor routes that cross the fault systems repeatedly. Extended outages in the transmission grid create cascading failures in the systems that depend on continuous power water treatment, sewage processing, hospital operation, communications infrastructure, fuel distribution. This is what the computer models are quietly computing, not as a prediction. As a consequence assessment, a systematic accounting of what happens downstream when two major fault systems fail in close sequence across a region of 60 million people and critical national infrastructure. It is the scenario that scientists don't want to say out loud. It's also the one their models cannot ignore. So where do we look in the coming weeks to know which direction the system is heading? So let me be direct with you about something before we close this out. I am not predicting a disaster. I want that stated plainly, without hedging it into ambiguity. No one can predict when an earthquake will happen. Not me. Not the researchers at USGS. Not the modeling teams at Caltech running the simulations we've discussed. What we've walked through together is science mechanisms, data, probabilities, and the honest limits of what those probabilities actually tell us. This is not prophecy. Anyone framing it as prophecy is doing something different from what I'm trying to do here, and you should be skeptical of them. What I can give you, honestly and specifically, is a set of signals worth watching over the next 2 to 6 weeks. Not because monitoring them will tell you when something happens, but because these 5 data streams represent the earliest readable indicators of whether the system is moving toward release or toward continued accumulation, and knowing the difference matters, even if it doesn't give you a precise answer. The first signal is slow slip event behavior under the Olympic Peninsula. The Pacific Northwest Seismic Network publishes SSE reports, and they're publicly accessible. What you're watching for isn't whether an SSE occurs. They occur regularly, predictably, roughly every 12 to 15 months in most segments. What you're watching for is an SSE that's anomalously large in displacement magnitude, or one that occurs significantly earlier than the expected recurrence window, or one that's accompanied by tremor activity at unusually shallow depths along the fault interface. Any of those deviations from the normal SSE pattern would suggest the stress distribution at the deep edge of the locked zone is shifting in ways the models didn't predict for this period. It wouldn't be proof of anything, but it would be a meaningful data point, and it's the kind of data point that tends to appear in retrospective analyses of sequences that preceded larger events. The second signal is microseismic clustering at the Salton Sea, specifically whether the M2 to M3 activity currently registering at the southern terminus of San Andreas increases in frequency, and whether the spatial distribution of that activity begins migrating northward along the fault. The 2010 Baja California sequence showed us what northward stress propagation from the southern end of San Andreas looks like in the seismic record. It's a recognizable pattern. If the current Salton Sea cluster starts producing events in a distribution that tracks up the fault rather than staying localized at the southern end, that directional migration is the thing to pay attention to, not the individual event magnitudes, which remain small, but the spatial trajectory of where the activity is concentrating over time. The third signal is lateral GPS deformation at UNAVCO stations along the West Coast. This one requires a little more technical context to interpret correctly, so let me be specific about the threshold. What you're looking for is horizontal surface displacement exceeding roughly 2 centimeters over a short time window, days, to a couple of weeks at stations in Northern California or Southern Oregon, without a corresponding SSE in the seismic tremor record that would explain it. SSEs produce a recognizable westward ground movement signature. If GPS stations are recording significant horizontal deformation and the PNSN tremor catalog isn't showing an SSE that accounts for it, that unexplained deformation represents stress redistribution happening through a mechanism that the standard models haven't characterized. That gap between what the GPS is measuring and what the tremor catalog is explaining is the signal, not the deformation alone, but the unexplained deformation. The fourth signal is volcanic seismicity in the Cascades, Mount St. Helens, Mount Rainier, Mount Hood. These 3 in particular sit directly above the descending Juan de Fuca plate, and their magmatic systems are fed by fluids released from that slab as it heats and mineralizes during subduction. The fluid budget of those volcanic systems is mechanically linked to what's happening at the plate interface below. Elevated volcanic seismicity, not surface deformation or gas emissions. Specifically, seismic activity beneath the volcanic edifices can reflect changes in the deep fluid dynamics of the subduction system. It's an indirect signal at one remove from the main fault interface, but it's a signal that connects to the same underlying machine. Any significant uptick in located seismicity beneath any of the 3 major Cascade volcanic centers is worth noting, not because eruption is the concern, but because of what changes in volcanic seismicity can indicate about subduction zone fluid behavior. The 5th signal is the quietest one, and in some ways the most instructive, precisely because of how rarely it gets mentioned in any public discussion of earthquake hazard. While water levels in coastal Oregon and Washington, this sounds low-tech. It is low-tech, and it works. Changes in groundwater pressure, including pore fluid pressure, changes along fault zones, have been correlated with anomalous well-level fluctuations in historical earthquake sequences, sometimes appearing days before the seismic events they preceded. There are community monitoring networks in both states where residents near the coast report unusual well behavior. These reports aren't definitive. They're noisy. They're anecdotal in isolation, and they require aggregation across multiple locations to become meaningful. But when multiple well reports from a coastal zone cluster in time, when people in different communities are independently noticing the same anomaly in their water levels in the same short window, that aggregated pattern has appeared in the historical record before significant events. It's worth paying attention to, and it's the kind of distributed observation network that only works if people actually know to look for it. Those are the 5 signals. Watch them not with fear, but with the same calibrated attention you'd give any system that you've taken the time to understand. Information, tracked consistently and interpreted honestly, is how you convert a vague sense of risk into something you can actually respond to. Which brings me to the part of this conversation that I think matters most, because understanding the mechanisms is only useful if it changes what you do. If you're on the West Coast of the United States, do one specific thing today, not tomorrow. Today, find the high ground nearest to wherever you sleep at night and figure out how long it takes to walk there from your front door. On foot? Without a car? In the dark? On potentially damaged pavement? With people around you who are disoriented and moving in multiple directions? Time it? Because that number, that actual, physical, tested time, is the most important piece of information you can have, and it costs you 1 afternoon to acquire. Cascadia's warning window to Oregon's coastline is 15 to 30 minutes from the end of shaking. Knowing you can reach elevation in 12 minutes isn't reassuring. It's the margin between categories of outcome. Beyond that, assemble a 72-hour emergency kit. If you haven't, FEMA recommends this for every household in the country, regardless of specific hazard type or geography. Water, food, medications, copies of documents, a battery radio, a flashlight. It's a recommendation so basic and so consistently ignored that public health researchers have studied why. The answer, again, is normalcy bias the same cognitive pattern we discussed earlier. It feels unnecessary until it's essential, and by the time it's essential, the window to prepare has already closed. Follow the USGS Earthquake Hazards Program and the Pacific Northwest Seismic Network. Not obsessively, not as a source of anxiety, as a source of information the same way you follow weather services not to live in fear of storms, but to know when to bring an umbrella. These are public resources. They publish data clearly. The monitoring community that runs them is doing the most important work in this space, and their public-facing outputs are accessible to anyone willing to spend 10 minutes learning how to read them. And then, and this one I want to emphasize specifically because the research on disaster outcomes makes it unambiguous. Talk to your neighbors. Have the conversation with your family? Not once. In a moment of anxiety after watching a video. Regularly. The communities that survive major earthquakes and tsunamis at the lowest proportional casualty rates are not the wealthiest ones. They're not the ones with the best individual preparation. They're the ones with the strongest social fabric, where people know each other's vulnerabilities, have agreed on meeting points and communication plans, and have rehearsed enough that the behavior under stress is automatic rather than improvised. A practiced community evacuation is worth more than 100 individual emergency kits sitting unopened in 100 separate closets. The Earth doesn't ask our permission, it doesn't consult our schedules, wait for convenient timing, or moderate its behavior based on how ready we feel. The tectonic forces that have been loading these fault systems for centuries will continue loading them until the geometry of the situation resolves itself violently, abruptly, on a timeline that no model can precisely specify. That is the honest summary of everything we've covered. But here is the thing that I want to leave you with, because it's true, and it's the part that actually belongs to you. The Earth doesn't consult us, but we get to decide whether we're ready. That choice is available right now. It will remain available until, at some point, that none of us can name. It isn't. The window between now and that point, however long it turns out to be, is not wasted time. It's preparation time. And what you do with it is entirely up to you. If you've made it here genuinely, thank you. Not as a formality. This was a long journey through uncomfortable territory, and not everyone has the patience or the curiosity to follow it all the way through. The fact that you did means something to me. Now, I want to hear from you. Where are you watching this from right now? Are you somewhere on the West Coast, close to everything we've talked about, or somewhere far away, watching this like it's someone else's problem? And honestly, did this land as a real concern for you? Or does it feel like we're overstating it? Tell me in the comments. I read everything, and I mean that. If you want to go deeper, there are 3 directions worth exploring next. The Cascadia tsunami in detail, specifically what the first 72 hours looks like on the ground for coastal communities. The full history of San Andreas, and why 1906 was actually the second time, not the first. And compound disasters through human history, the moments when nature struck twice, and what separated the survivors from everyone else. Drop a comment below and tell me which one you want to see next. I'm letting the comments decide. And if this video reached you in some way, if it made you think or made you feel something real, hit a like and a subscribe. I'll keep watching the signals. When the data says something worth saying, I'll be back. This story doesn't end in one video. See you next time.